So today we're going to look at the Sherwood-Gilliland correlation as it pertains to a cylindrical pipe with water flowing down the sides and air blowing up in the middle. So how we're going to do that is through dimensional analysis. So what we want to look at is the three fundamental units: kilograms, meters, and seconds, and relate those to the variables pertaining to this problem. So we'll have the mass transfer coefficient, which has units of meters per second. We'll also have the velocity, which also has meters per second. And then we'll also look at the density, which has kilograms per meter cubed. And then also the viscosity, which has units of kilograms per meter times second. Then the diffusivity coefficient, which is going to have units of meters squared per second, and the diameter of the pipe, which is in meters. So we have 1, 2, 3, 4, 5, 6 variables and 3 fundamental units. So now the dimensional analysis looks at the units and determines if they're in the denominator or numerator. So for the mass transfer coefficient, we don't have any kilograms. Then we have a meter in the numerator and a second in the denominator. Same for the velocity. Then for the density, we have 1 kilogram in the numerator and 3 meters in the denominator and no seconds. Then the viscosity has 1 kilogram in the numerator, a meter, and a second in the denominator. Then for the diffusivity coefficient, we have no kilograms. We have 2 meters in the denominator and 1 second in the 2 meters in the numerator and 1 second in the denominator. Then for the diameter, we don't have any kilograms. We have 1 meter and no seconds. So now what we're going to do is we're going to assign the core group, which is, we will define that as the mass transfer coefficient, the velocity, and the viscosity. Then now we are going to establish the rank of the dimensional analysis, which is the rank is equal to the variables minus the core group. So we have 6 variables and 3 core group. Within the core group, one of every fundamental unit must be incorporated. So that gives us a rank of 3, which means that we're going to be calculating pi 1, pi 2, and pi 3. Now, pi 1, 2, and 3 are going to be dimensionless groups, meaning that all the units in those formulas will cancel out. So now we just plug pi 1, 2, and 3 will contain, each one will contain non-core group values, then 1 of every core group value per formula. So we're going to say pi 1 is equal to the diffusivity times the density times the diameter. Then our core group value for 1 will be the mass transfer coefficient. So it'll be diffusivity raised to the A, density B, and diameter C. Then pi 2 will be equal to the diffusivity D raised to the D, density raised to the E, diameter raised to the F times the velocity, and pi 3 will be the diffusivity raised to the g, the density raised to the f, or h, and then the diameter raised to the I times the viscosity. Now, what we're going to do is we're going to look at the units involved in each relationship to determine whether or not that variable will be in the numerator or the denominator of the correct equation. So the units of pi 1 will be meters squared per second raised to the A times kilograms per meter cubed raised to the B times meters raised to the C times meters per second. Now, all of these units must cancel out. So there's only 1 kilogram in this expression, which means that the power B must be equal to 0, which eliminates the units for density. Then also meters must cancel out and seconds must cancel out. So A has to be inversed. So A is equal to -1 and C is just equal to 1, which results in pi 1 equaling the diameter times the mass transfer coefficient divided by the diffusivity from A to B. And that expression, through definition, is defined as the Sherwood number. Now we're going to look at pi 2. So the units of pi 2 are going to be equal to the diffusivity, meters squared per second raised to the D, times the density, kilograms per meter cubed raised to the E, times the diameter in meters raised to the F, times the velocity, which is meters per second. Now, just like pi 1, pi 2 only has 1 kilogram in the units, so E must be equal to 0, and then the seconds must cancel out and the meters must cancel out, so D is going to be in the denominator, so D equals -1, and then F just equals 1. So then that gives us pi 2 as the diameter times the velocity over the diffusivity from A to B, which that is equal to the PE number times the diameter. So then for pi 3, for the units, we're going to have the diffusivity, meters squared per second, raised to the G, times the density, kilograms per cubic meter, raised to the H, times the diameter in meters, raised to the I, times the viscosity, which is kilograms per meter second. And now all the units have to cancel out. So in order to cancel out the units, we know that the kilograms must cancel, and since there's no power here, we cannot determine if this viscosity must always be on the numerator. So looking at the density, we can determine that that is on the denominator, making H equal to -1, which then allows the kilograms to cancel out. Now, in order for to get to the meters to cancel out, we also have to make the diffusivity or g, the power g, also -1. So then now we have g is also -1. Then if we just count up our meters, we have 1, 2, 4 on the numerator and 3 on the denominator, which means we have 1 extra meter. So what we're going to do, I, the power of I, if we make that equal to 0, then all the units cancel out, which results in pi 3 as the viscosity over the diffusivity of A to B times the density. And that one is going to be equal to the Schmidt number by definition. So now we have the Sherwood, the Schmidt. In order to get the Gilliland and Sherwood correlation, we also need the Reynolds number. Now the Reynolds number can be determined by dividing pi 2 by pi 3. So if we write pi 2 divided by pi 3, pi 2 is equal to the diameter times the velocity over the diffusivity of A to B, divided by pi 3 is the viscosity over the diffusivity A to B times the density. Now, the diffusivities cancel out, and we are left with the density times the diameter times the velocity over the viscosity. And that is equal to the Reynolds number. Now, looking at our scenario of having a wetted wall pipe with air blowing across it, we determine that these 6 variables relate to the mass transfer within this system. And then we did dimensional analysis to determine the Sherwood, Schmidt, and Reynolds number. And now that leads us to the Gilliland-Sherwood correlation, which is equal to, which states that the Sherwood number is equal to a constant A times the Reynolds number raised to a constant B times the Schmidt number raised to a constant C. Now that we have that, once we determine A, B, and C for this correlation, we can determine the mass transfer coefficient within this system. And that is what we will be doing in the coding section of this problem. Thank you. Okay, so now we're going to move on to the coding portion of the problem, looking at the Sherwood-Gilliland correlation. We're going to use a 10% error as we generate our data, then use linear regression and sum squared error to find coefficients A, B, and C. Then we're going to use a 3D model to plot it. So first thing we're going to do is we're going to import numpy, numerical calculation, as np, then from scipy.optimize, we're going to import minimize, which will be for the sum squared error. Then we are also going to, from plotly dot subplots, we're going to import make subplots. Then we are also going to do import plotly dot graph objects as go, and then we're also going to import just for like a filter for the graph, we're going to say templates default is equal to plotly dark. So that's just importing all of the behind the scenes calculations that we need. And then now we're going to generate our data, saying that the Reynolds number is going to be to a set of random uniform numbers with the ranges of 2,000 to 35,000 with 100 points, and the Schmidt number will be the same, and the range is 0.6 to 2.5 with 100 data points. Then the Sherwood correlation equation as defined in the textbook is 0.023 times the Reynolds number raised to the 0.83 times the Schmidt number raised to the 0.44. Then we want a 10% error, so we're going to say Sherwood number is equal to random dot normal distribution, and the lock is going to be equal to the Sherwood correlation number, and the scale will be the 10% error times the Sherwood correlation. So that gives us our data. Now we're going to move on to the linear regression method. In the linear regression, you use matrices to calculate A, B, and C by taking the natural log of the equation. So you'll take the natural log of the Sherwood number, Reynolds number, and Schmidt number to get those coefficients out front, and then you can calculate the actual number for those coefficients. So I say x is equal to np.columnStack, and for the first we're going to say np one's like the Sherwood number, and then we're also going to do log Reynolds number and log Schmidt number. Make sure that's right. Okay. And then now to calculate this, we're going to say np dot linout dot inverse, and we're going to take the transpose multiplied by the matrix multiplied by the transpose multiplied by the log of the Sherwood number, and that's going to give us the coefficients A, B, and C. So to determine the actual numerical value, we're going to print B, but since the coefficient C is just the natural log of where you want to take the exponent, so we're going to take exponent of B, the first term, and then there we have. So we have coefficients A, B, and C, where this is the natural log of, A. So this is the natural log of A. So we're actually going to exponent that, take that to the exponent to get the actual number of A, B, and C. So that's the linear regression method. Now we're going to do the sum squared error method. So for that, we're going to define sum square P. Now we know that the constant absolute error equal to the np dot sum of the Sherwood number minus the correlation. So it would be P0, that'll be the first term, times the Reynolds number raised to the second term times the Schmidt number raised to the third term raised to the, or squared. Now this absolute constant absolute error. So what we want to return the relative error. So it's going to be the same equation manipulated just slightly. So it will be this equation, and we're going to divide that by the Sherwood number squared. Now that gives us the sum squared error. Now what we want to do is we want to minimize the sum squared error and the correlation to get the number, the value of A, B, C. So we're going to minimize sum squared and the error, the correlation. So that's the correlation, that's the coefficient A, coefficient B, and coefficient C. That gives us that, and then res.x will give us the set that we're looking for. There we go. So 255, 24, 8, 81, 82, 45, 45. So they're relatively the same. If we restart and run all, it will run everything together, giving us relatively the same numbers for the exponents. Here we go. 1.8, 1.9, 1.86, so that's relatively 1.9, 8.4, 8.4, 4.3, 4.3. So relatively the same. So now we move on to graphing this as a 3D model. So these are this here is the coefficients A, B, and C, and this here is the coefficients A, B, and C as well. So we're going to create a figure that is equal to make subplots, and within that we're going to add the trace. We go dot scatter 3D, where x is equal to the Reynolds number, y is equal to the Schmidt number, z is to be equal to the Sherwood number, and we want this as we want this in the form of markers, and then we also are going to adjust that marker size to be 5. And then our marker color will be the Sherwood. And then our marker opacity will be equal to 0.9, found in the example in class. And then our marker line width we want to be 1. And then we want our marker line color to be equal to white. Alright, so now we have that trace. Now we want to create a mesh grid. In order to create a mesh grid, we first need to define SC number grid, and the Reynolds number grid will be equal to np dot mesh grid. So the first term is the Schmidt grid, so we're going to say np dot lens space, and then the range of the Schmidt number is 0.7 2.6 to 2.5. We want 30 different grid lines. And then now the Reynolds number, np dot linspace. Reynolds number is 2,000 to 35,000 with 30 grid lines. And then now we also want the Sherwood grid. And because the correlation, we can use the line above this one to create the Sherwood grid. So this will just be equal to res x of 0, so the first exponent, or the first term in this result. So of 0 times the Reynolds grid raised to the x of the second component times Schmidt grid raised to the third component. Now we have a mesh grid. So these are grid lines for one direction. I believe this is the horizontal direction. So what we want to do is we want to pair up each grid line with each data point. So in order to do that, we're going to say for the Reynolds, Schmidt, and Sherwood, and we're going to zip them together, which pairs two components at a time. Reynolds grid, Sherwood grid, or Schmidt grid and Sherwood grid. And then now we need to basically adjust that plot a little bit. So we're going to fig.add trace for go.scatter 3D, where x is equal to, then y is equal to the Schmidt, and z is equal to the Sherwood. And for the mode of the grid lines, we want the mode to be in lines. And then to determine the line, we want that to be, we want that color to equal 0.065 pound defined in class. And then the width of the line to be equal to 2. And then, so this section here creates lines in the horizontal direction that pairs 2 points at a time, varying. It pairs the Schmidt and the Reynolds number as it varies the Sherwood number points. So now we're going to do that same thing but in the vertical direction. So in order to do that, we just copy this down, and we have to switch the order of the Reynolds number grid and the Schmidt number grid. And then we have to adjust the parameters. So for Reynolds number is 2,000 to 35,000 with 30 points, and for the Sherwood number will be 0.6 to 2.5 with 30 points. The Sherwood number, or the Sherwood grid, will remain the same, because the equation doesn't change. And then we also are going to copy this down, and this stays the same as well, because this just creates the line. So now the sum of those two will create a hash grid. And then in order to just modify the graph a little bit more, we're going to fig.update layout. We're going to make the width of this plot equal to 800, and height as well equal to 800. And then we also we don't want a legend to show, because it basically makes everything cluttered. So we're going to say show legend equal to false, so it won't. Then we also want to put the axis titles on there. We're going to say the scene is equal to dictate axis title is equal to the Reynolds number as defined above. Then the y-axis title is equal to the Schmidt number, and the z-axis title is equal to the Sherwood number. Now, that should give us a 3D model showing the correlation of the Gilliland-Sherwood correlation in regards to the experimental data, and plot it out. Smallest things get me every time. Okay. Oh. Marker line width. Oh, misspelled there. Marker width. There we go. And certainly something else as well. Oh, it's misspelled again. Is it? Wait, where was that? Marker line width. Yeah, so marker line width, there we go. So now, there we go. So here is a 3D model showing the Sherwood, or the Schmidt number, and the Reynolds number, and the Sherwood number. So if you look here, you can see Reynolds number going in a horizontal direction, and the Schmidt number going in the vertical direction, and the Sherwood data points are varied throughout that grid. So that's what we did right here, all of this. So this shows the Sherwood-Gilliland correlation with a 10% error for the data that we generated. Yep. And there you have it. We can look at how points vary from that grid, and each point will tell you X, Y, Z. So for one point, you can find that. Sure. So for this point here, we have Reynolds number as 19,000. Looks like the Schmidt number as 0.9, and the Sherwood number is 78. So that sums up our problem. Thank you.